All right, Unit 3, Day 2, more polynomial review. Okay, so real quick, let's go through what we did in Day 1 notes. We're going to sketch a graph. So the first thing we need to do is identify our zeros. So I have x equals 0, x equals 8, and x equals -6. X equals 0 is odd, so it'll be a crossing 0. Same thing with x equals 8, and it will be definitely flatter at the point because of the high degree of 7. And x equals -6 will be a touch. Since it's an even multiplicity, and it'll be somewhat flatter, but not real flat at that point. Next thing we need to know is our highest degree. If I add my exponents, I get 11 plus 3, I get 14. So even. And my lead coefficient is -12. So my end behavior is going to be down on the right, down on the left. All right, so let's see if we can sketch this graph. So start with your end behavior, put your zeros in there. So I'm going to have a 0 here, that'll be a cross. I'll have one at 8. That'll be a cross. And at -6, I'm going to have a touching 0. Okay, so on the test, I really don't want you to put the T's and the C's for touching and crossing. I'm just doing that as a reference so I can remember what to do. Okay, so remember at basically all of these except x equals 0, they're going to be a little bit of a flatter 0. So at -6, I'm going to have kind of a flat touch there. So then at 0, not going to be terrible. And then at 8, it's going to be somewhat of a flatter 0 because of the number of multiplicities you have. So there's a sketch of that graph. So now we're going to work backwards. We need to create a polynomial that could produce this graph. Okay, so my end behavior, I know I need even degree and a positive lead term. Since I'm up on the right, up on the left. So then if I identify my zeros, here I got x equals -6, and it's a crossing 0. So that needs to have an odd multiplicity. Here I have x equals 0, and it's a touch, and it's a flatter touch, so a higher even degree. And then here I've got x equals 4 with a cross. So if I want to write a polynomial f of x, I know I'm going to have an x out front and an x plus 6 and an x minus 4. I know my lead term has to be positive, so I'm okay with just leaving an x sitting out front. I could put a number in there in front if I wanted to. I could put a 2. It's not going to change the outcome. I still have a value at x equals 0. This one is a touching 0, so I'm going to make it 4th degree because it's a little bit flatter. And then I have crossing. So if I just leave those as a 1st degree, I have my positive lead term, which is 2. And then I have my even degree. I've got a 4, a 5, and a 6. So that would work pretty well. I don't want to make those odd degrees any higher because those crossing zeros are pretty much straightforward. They're not too flat. So probably the best bet is to just leave it first degree. All right, so we're going to look into what's called the rational zeros theorem. In the world of Algebra 2, I can tell you that I did not cover this. College algebra, you may or may not have discussed it. I'm not too sure. But the rational zeros theorem is a way to identify possible zeros of a polynomial. So before the world of graphing calculators, this was something that was a definite necessity so we could find zeros of a polynomial. Now we know we can graph them. So in order to get my rational zeros list, possible rational zeros, I take the factors of the constant over the factors of the leading coefficient. It's not a difficult task, but sometimes it produces a rather large list of possible zeros. All right, so I'm going to take my factors of the constant, which is 21, over the factors of 9. Okay, so if I do that, numbers that go into 21 are 1, 3, 7, and 21. It's always a good idea to put those in order from smallest to largest. And then the factors of 9 are simply 1, 3, and 9. I also have to remember that I can have positive, negative factors. So all of these are going to have positive, negative symbols in front of them. In other words, I could take a -1 times a -9 and get a +9, or I could take a +1 times a +9 and get a +9 as well. So then if I break these apart, I'm going to have a pretty comprehensive list. And I just usually start here. And I'm going to put 1 over 1, which is 1, 1 over 3, which is 1/3, and 1 over 9, which is 1/9. Then I go to my 3. I put a 3 over 1. If I put a 3 over 3, I've already got 1, so I don't need to put that again. 3 over 9, I've already got 1/3, so I don't need to put that one. Then if I put 7 over 1, and then I have 7 over 3 and 7 over 9. So then I go to my 21, I put a 21 over 1. 21 over 3 is equal to 7, so I don't need that. And 21/9 is equal to 7/3, so I already have that one. So my possible rational zeros, I've got 1, 2, 3, 4, 5, 6, 7, 8 times 2 because it's positive, negative. So I've got 16 possible rational zeros. So if you wanted to find a zero of this polynomial, you would go to your calculator and use the calculating feature to find a zero, start breaking it down. In the world of your older teachers, such as me, we did not have graphing calculators. So once we got our list, we just started and we synthetically divided over and over again until we could break our polynomial down to quadratic. So it was a tedious process. And none of those zeros may work. So that created another issue for us. All right, so here I'm going to put my factors of 2 over my factors of 6. So that's not going to be a very long list here. We got ±1, ±2 over 1, 2, 3, and 6. So if I break those apart, I get positive or negative 1 over 1, which is 1, 1 over 2, 1 over 3, and 1 over 6. And then I go to my 2 on the top. I have 2 over 1, I have 2 over 2, which I already have. 2 over 3, and 2 over 6, which reduces to 1/3, so I already have that one. So here I have 1, 2, 3, 4, 5, 6 times 2. I have 12 possible rational zeros. If you recall, the degree tells you how many zeros you're going to have total. So you've only got 3 on this one, and this one would have 7. Some of them can be irrational, and some of them can be imaginary. So that list will only help you break down rational zeros. All right, so for this last one, I got factors of 10 over factors of 4. Factos, forgot my R in there. So for 10, I've got 1, 2, 5, and 10. Positive, negative for all of those. And for 4, I've got 1, 2, and 4. So you can see if your numbers have a lot of factors, then you get a larger list. So here, if I start with my 1, I've got 1 over 1, 1 over 2, 1 over 4. If I go to my 2, I've got 2 over 1, 2 over 2 I already have, and 2 over 4 I already have. So go to my 5, I put 5 over 1, 5 over 2, and 5 over 4. Then I'm at my 10, so I've got 10. 10 over 2 is 5, I already have that one. 10 over 4 reduces to 5 over 2, so I already have that one. So here I've got 1, 2, 3, 4, 5, 6, 7, 8 times 2, 16 again. Remember, these are only rational zeros. You can also have real, irrational, and imaginary. Okay, so there's your rational zeros test. All it is the factors of the constant over the factors of the lead term, plus minus for all of them, and separate them out. All right, so equivalent statements of polynomials. So if you start here, x minus c is a factor of f if the remainder is 0 when you synthetically divide. So if that's the case, c comma 0 is an x-intercept. Intercepts are always written as ordered pairs. If it asks for a 0, such as here, then it would just be x equals whatever that value of c is. And here is just function notation, f of c is 0. Okay, so all of those mean the same thing when you're talking about zeros of a polynomial. When doing synthetic or actual polynomial division with c, the remainder is 0, c is the 0 of the function. So we do synthetic because it's quicker. Long division is the actual polynomial. That in both classes, I'm sure that you took before this one. Synthetic is quicker, but you can only do synthetic when you're dividing by one single 0 or a linear factor. Okay, so let's go through synthetic and see if we remember how to do that. So we're determining if x equals 1 is a 0 of the polynomial. So if you recall, if your highest degree is 3, when you set up your synthetic division, you could have 4 terms at the top. Okay, so then you go through and you ignore your variables and you just write down your coefficient. So 2, -4, 8, and 4. I'm sure this will come back to you if you've forgotten it. So right here, degree 3, right here, always 1 more than your highest degree number of terms. Okay, so first step is to bring down your 2. Then you multiply. 1 times 2 is 2. and then you add. -4 plus 2 is -2. Multiply again. 1 times -2 is -2. Add, you get 6. 1 times 6 is 6. 6 plus 4 is 10. This is your remainder. So since your remainder is not equal to 0, x equals 1. Oh, I don't know why I put a negative there. X equals 1 is not a 0 of f of x or t of x. Because the remainder is not 0. If your remainder was 0, then you actually would have a point on the x-axis, which tells you that that number or that value you synthetically divided by is the 0 of the function. All right, so in this one, now I'm determining if x plus 1 is a factor. So if x plus 1 is a factor, then x equals -1 is a 0. So that's the value you divide by. So -1 outside. My degree is 4. So I should have 5 numbers that I'm writing down. So if you look, you're only going to have 1, 2, 3, 4. So I am missing a term in here. I'm missing x squared. So I have to do a placeholder for that and put a 0 in that place. So I'm going to have 3, -5, 0, 2, and -6. So there's 1, 2, 3, 4, 5 terms. Make sure they're in order by degree. So my 3 comes down, I multiply, I add. -1 times -8 is 8. I add, and I get 8. -1 times 8 is -8. I add, and I get -6. -1 times -6 is 6. I add, and I get 0. So this is my remainder, which tells me that x plus 1 is a factor of p of x. And x equals -1 is a 0. All right, so hopefully that rings a bell. It's going to help you break down polynomials as we move on through the unit. Have a wonderful day.